All right, so it goes from nanometers and it goes over to meters. Which one's bigger, nanometer or meter?
Meter.
Okay, so it goes from nanometers, which is small, to meters, which is large. So he has the right idea, but it goes from a short wavelength to a long wavelength. Okay, does that make sense? What happens to the frequency? So what happens to the frequency?
It gets smaller.
It gets smaller. Okay? So do you guys see a trend? It goes from short wavelength to long wavelength, and then on the frequency, it goes from high frequency to low frequency. What is that relationship? The longer the wavelength, the lower the frequency, and that's called what kind of relationship? We talked about it yesterday. We did a graph. We did a table. Remember? Yep. I wrote a table on the board. Whether you wrote it in your notes, it doesn't really matter, but I wrote a table on the board. Because it was 3, 1.5, and 1 meter long spring. Yep, and then we had frequencies went up. So what do we call that? Inverse. Okay, you'll be hearing that a lot. So, inversely related. You might have a question on a test that says, what's the relationship between wavelength and frequency? And you'll go, okay, if the wavelength gets shorter, then the frequency goes up. It's got to be inverse. Okay? So, I'm going to write this down, and just go ahead and put this chart down real quick. So down here, it goes gamma. Then what's next? What's next? X-rays. Then UV. Now these are all high frequency waves. They're high energy waves. So down here we have high frequency. Okay, that's the high frequency down here. Then we go V. So we got visible. So the visible goes what? V, I, B, G, Y, O, R, right?
Yeah.
Okay?
No.
Is that how it goes? Violet, indigo, blue, green, yellow, orange, red.
There's not. Yeah, the book doesn't say indigo.
That's okay. I'm going to put it in there.
Oh.
All right? Yes? Okay? Yes?
Could I just write up what you did?
If you do, it would be wrong because we want to write it in the order from high frequency to low frequency. You can write it, you just write it backwards. It's Roy G. Biv backwards. Okay? It's kind of like, what was that? The Stephen King novel, when they're in the hotel and they get snowed in. You guys, anybody see Shining?
Yeah.
The kids always saying red rum, red rum, red rum. You know what that is backwards, right?
Murder.
Murder. Okay? Roy G. Biv. Alright? Then we go IR. Okay? Then after that we'll go radar. So, radar was a tremendous invention and a process in World War II that they came up with that probably saved a lot of people's lives because they could tell beforehand if a raid was coming in or something was happening. So it was an unbelievable invention that took place in which, and they did a lot of work with it, but radar waves would be there. Then you kind of got FM and television waves. And you got short waves. You guys ever heard of shortwave radio? You can communicate with somebody over the radio or communication, not the cell phone. It's not that big a thing anymore, but it used to be where if you wanted to communicate with somebody a long distance, you do it through what's called a shortwave radio. That's what you would use. Okay? And then you'd have long wave. Right? So this side of the spectrum, we got high frequency. This side of the spectrum, we have low frequency. Okay? Vice versa, on this side, here, up here, you have short wavelengths. And down here you have long wavelengths. Now, here's a trick question that you'll see on the test probably. Okay? Now think about it before you answer. How does the speed of X-rays compared to the speed of green light? What's their speeds? How do they compare?
Isn't the speed of light the same, so all the same?
Right. So that's kind of a trick question, right? So I'll say, which one has a faster speed? And you'll go, neither one have the same speed. Okay? But if I ask you which one has a higher frequency, X-rays or green light, you'll say X-rays. Down here. Down here. So this side, high to low. I love this stuff. I don't have to erase it. Okay? Questions you have on that? All right, I'm going to have you do a little reading, not too long. I don't want to take too long on it. We'll refer back to that from time to time. If you guys would turn your attention to page 102. 102, I would like you to read the paragraphs all the way, the first 3 paragraphs, please. Which takes you to the bottom of the page, and I'd like you to take a look at the chart down there, and we'll talk about that chart and what that means. When does the electron that's in the ground state, when can it jump up to the excited state? What's going to happen? Yeah, when it brings in energy. Absorption of energy. So we have this arrow that can represent energies directed at that electron. Okay? And that would be energy in, and that would be absorption of energy. Okay? Absorption of energy. I'll just put E for energy. So absorption of energy is going in. Now, what's going to happen to that electron once that energy is absorbed? It's going to stay there.
It's going to move up a ring.
It could move, if it's enough energy to move up a ring, it will do that. Now, here's the analogy. If I send Tanner, I say, Tanner, here's a quarter. I need you to go get me a pop. And he's going to look at me and go, what are you doing? Man, I need more than a quarter. Okay? This isn't 1955. All right? So, I need to give you $1 with that. So I give him $1.25, and he goes gets a pop, and it says $1.25, and he puts $1 in, and he pushes the button. Nothing happens, right? He has to put in what? $1.25. Now, if I didn't have $1.25, I have $2. I said, Tanner, go give me a pop, and give him $2. Can he get the pop? Yes. Yes, he can. So it has to be enough energy that it has enough energy to pop it up to an excited state. So E2 would be an excited state. Now the thing is, it won't stay at that excited state. It will always want to get back to ground state. right? It always wants. So now you got to think. There's lots and lots of these atoms gaining this energy, and they're all doing the same thing. And so this one will go up, but then once that energy level doesn't come in anymore, then it goes back to the ground state. When it goes back to the ground state, we have this thing called conservation of energy. And so something has to be emitted off. So we're going to go ahead and show that emission with this, with a wave. Okay? And then, so this would be energy emitted. Okay? So we have emission of energy. So we got energy emission. Now, this is a wave, and if it's in the visible spectrum, we could see it. It could be in the visible spectrum, it could be outside the spectrum, it could be ultraviolet, it could be infrared side. We really don't know, but we just know that there's an energy emitted, okay? So let's say that this same electron, there's enough energy to go into it to allow it to go to a higher energy level. Okay, even higher. Okay, when it goes higher, that means more energy is going in. If it drops back down to that ground state, what do you think the wave length is going to look like compared to this wavelength? Is it going to be shorter, or do you think it's going to be longer?
Longer.
Okay, why do you think it's longer?
Because then that means frequency is smaller, and that means less energy.
Okay, but if it's kind of like a book dropping from a level and then from a higher level, which one do you get more energy out of? One from a higher level, right? So is it dropping at a greater distance than the first one? So if it's dropping at a greater distance than the first one, it has more energy. You are right, there's more energy, but the wavelength's going to be shorter. Because what do we know about short wavelengths and energy? Like gamma rays and X-rays, what do we know about? Are those harmful rays? Yeah, why are they so harmful? They have high energy. They're very high energy waves. Okay? And so this would be also emission, but it's a shorter wavelength. And so when you have bigger energy jumps, then you have higher energy associated with it. Does that make sense? Look at the drawing at the bottom of page 102. Is it pretty much, it doesn't really show multiple waves, but it kind of, this is, I think mine kind of shows you two scenarios. Okay, what the next thing I'm going to do, we're going to do a couple problems dealing with frequency and energy, and then I'm going to give you some ample time to work on it. Okay? So, the next slide, what I'm going to do is I'm going to go ahead and give you a word problem, and then we'll talk about the word problem. We're going to do two of them. 2 word problems. So this is Bohr's model. It's an explanation of how atoms give off energy when they absorb energy. And tomorrow we'll do the flame test lab where you're going to go ahead and put different things into a flame and get different colors off when you do that. Okay?
What? But you're always right. You're literally always right.
I'll put it back.
Oh yeah, I agree with you. How do you hear everything I say?
Every
Like,
night,
even the lowest
except for
point, and you
Wednesday
will still hear me.
and Friday.
That's funny. Oh my gosh.
And they got, I got
Oh, really?
That's funny.
Do you have college?
I have no experience. I had 6, but I switched out of that because I wanted to stay with my class.
I like college. I'm not getting on all my conversations.
You as well?
I know people hate Welsh. You're so slow. Call them very fast.
College bowl,
I don't mind.
I don't like so slow because this Syracuse is like PowerPoint's a lot more than we did last year.
I like it.
Yeah, I love it.
Okay. Guys, we're going to take about 5 minutes to finish this up, and then you guys have time to ask questions, to work through problems. Yesterday, I gave you an equation. You're going to have to use a possibility of 3 different equations. First one we're going to look at is the equation that C equals lambda times nu. C is 3 to the 8th meters per second. That is the speed of light. Wavelength I'm giving you is 410 nanometers. And we're asked to solve for the frequency, and the frequency is unknown. Okay? So, what do we need to do before, give me some ideas what you would do when you go through and set this up. Yep, got to get V by itself. So we go ahead and get V by itself. So V equals what? C divided by wavelength, right? Does everybody see how we got that? We divide both sides by wavelength, we solve. Okay. What's the next thing we need to do?
Change the units.
Change the unit. Right. Change the unit. We can't put nanometer in there, right? Because this is in meters, and so everything has to be in units of meters. So you guys already know that when we do that, we go ahead and put nanometers down below and meters above, and we compare them. So for every 1 nanometer, how many meters do you have? 1 times 10 to the what? The what? -9. Right? We do the calculations. You guys want to practice calculations with scientific notation because some of you struggle with that. You don't have to. You're going to get a number out. That would be 4.1 times 10 to the -7th meters. So if I plug that in, that's what I'm going to get in meters. So I convert it to meters, and now I can plug my numbers in. So what I would do is I take 3 to the 8th, meters per second, divide by 4.1 times 10 to the -7th meters, and I'll get my answer. And I think it's like something to the 14th. Might be like 7 to the 14th. Okay, when you do that. So you're just setting up the speed equation in which to solve for different values. So it's 7.3 to the 14th. Any questions on that one? Hertz, right? Questions? Yes.
But why would it be times 10?
When you subtract exponents, like if on the calculator, what it'll do when it divides exponents, it'd be 8 minus a minus 7. So it'd give you a number times 10 to the 15th. And when you take 3 divided by 4, you get 0.73. So if you did this in your head without using the calculator, you go 3 divided by 4. When you do that, you're going to get 0.73. And then when you take exponents, 8 minus a minus 7, you get to the 15th. You move your exponent over 1. Then it would be 7.3 to the 14th. So when you plug it in your calculator, that's what you're going to get. But you can also do it in your head. You don't have to use a calculator to do it. Any questions on that? Makes sense? Yes?
I kind of understand the concept, but I still get tripped up for some reason how, like, you change the equation.
Changing this equation?
Yeah.
You just have to isolate V. And it's just a linear equation, right? I mean, I'm helping freshmen go through and do this in an academic study hall. That's all you're doing. You're isolating a variable. And then you're solving for it. That's all you're doing. Okay? Next one. I need to give you 2 equations. The next is dealing with energy. If you guys look at the bottom of page 102, you guys see the bottom of page 102, they give you an equation. And that equation is E equals what? Of a photon equals H times what? V. Okay, so E stands for energy. And anybody know the label for energy? Joules. Okay, so now we're gonna calculate energy with frequency. If we know the frequency, so there's a direct relationship. The higher the frequency, the higher the energy. That's like gamma rays and X-rays. That's kind of how they work. Now H is a constant, like speed of light is a constant. H is called Planck's constant, and it's equal to 6.626 times 10 to the minus 34. Joules times seconds are their units. So every time you plug in H, you want to plug in 6.626 to the minus 34. Okay? You don't have to remember them. You'll be given all constants. Okay? Right? You'll be given the equations. You don't have to memorize the equation. I'm going to give it to you. I'm going to give you the constants. Okay? So, to set up to solve for frequency, what would it look like? So, I'm solving for V. So, V, frequency, equals what?
V divided by H.
Okay? So it's going to be E divided by H. Very good. Go ahead and do that and see what you get. Should get a number to the 14th again. Hertz. Should be 6.8 times 10 to the 14th. Okay. So what I'm going to do is